let's continue with the last session of today, where the first speaker is Giuseppe Bruno. I had mentioned that already in the opening, that Giuseppe, together with Jörg Eichelin, is coordinating in the Strong 2020 project the heavy flavor related activities, and Giuseppe will give us an overview.
Okay, thank you, Ralph, and thank you all the organizers for giving the chance to briefly introduce about this project. So, outline, I will tell just a bit more in general what is this large Strong 2020 project, and then one of the work package within this project, this networking activity, HFQGP, its structure, objectives. And I will mostly concentrate on a discussion we started 2 weeks ago for using some tool for facilitate the data to model comparison. So Strong 2020 is this big project on hadron physics, the strong interaction of the frontier of knowledge, fundamental research and application. It's an European project. The coordinator of the project is Barbara Erasmus. Here you have a link to the project where you can find a lot of details of the work package and so on. So it counts now 45 participating institutions from 16 countries in Europe. Of course, participation also from abroad in Europe is welcome. Was not possible to be direct funding, but this is actually already happening within the project. So as I was telling a moment ago, you see the large budget, about 10 million euros. It is subdivided in 32 work packages, one for management, one dedicated to dissemination and communication. It has 7 traditional, as in previous project like this one. This transnational access to research infrastructures in Europe, and now also 2 virtual access to virtual infrastructures. And then a number of 21 more traditional work packages, either joint research activities, where I typically do R&D on detector, not just data, but mostly, or activities more in the direction of networking, to facilitate the exchanges, the meeting, the visits. So just last slide on this big project, and I will specify a bit more on the networking. So the ACQ Star, the Trento Center also entered in this transnational access. And in this edition, there is also possibility, there has been this possibility to have the virtual access. There are 2 of such packages. Both of them, I would say, quite related to our field of research. So the aim of this virtual access is to provide open access to state-of-the-art computer codes for ion reaction, the study of the dual plasma, as well as for nucleon and nuclear pattern structure research. Those are the 2 coordinators of these virtual access activities. So one of these 7 networking activities, HFQGP, the full name is for Gluon plasma characterization with flavor probes. The main objective is to support a joint effort of experimentalists and theorists in characterization of the QGP, mostly at LHC energy, using heavy flavor observables. There are 2 coordinators, Jörg and myself. We receive a budget. This is mostly for meetings and mutual visits, but also about 1 year of postdoc in theory in expect. So we have structured this networking activity in 3 subgroups, open heavy flavor, and in each subgroups we had conveners, both experimentalists and theorists. And from the experimental point of view, we try as much as possible to give representatives to the different LHC experiments, mostly because this is an European project with the focus on the LHC physics. So Penelli Flavor, Andrea and Salvo, which I think are present today. For the Quarkonia conveners, Emilien Chapon and Enrico and Alexander. Roshkov, for small system, Zaida, Benjamin Oduhe, and Andrea, which is also connected today. There is a mailing list. Of course, you are really welcome to subscribe to follow the next actions. So I come to next actions. We also have a workshop this year at ATC Star towards the end of this year, in November, with title called One Plasma Characterization with really clever probes. Hopefully, this will be done in person, and we discuss with you. Most of you, of course, are already being contacted for that. It will be a pleasure to have a meeting together in person, if possible. If not, it will be virtual as this one. So we plan to have a report with prospects and recommendations for the ideal periods in the next rounds. And also, and this I would discuss a bit more in the following, we propose to have a tool to facilitate the comparison of theory and experimental results in the HF sector. And this networking activity has some budget, not that large, so those kind of things we would like to push and support. So at the beginning of April, actually we start to discuss about that. We planned when we contacted the organizer of this workshop, we wanted to start to trigger the first discussion at the time when your workshop was supposed to be in Trento last year. So something we have done, of course, in the meanwhile. So we had this dedicated workshop because we selected Rivet as the natural framework to further develop this tool or to give support for this in this direction. So here I put the indico agenda of the workshop we had. We had the contribution from the Rivet developer teams, the core developer teams, from the main authors of event generators in the field of Alliance, Epos, PHSB, Smash, QCD, 10 presentations from the main LC experiment, Alice, the other CMS, LCB, GSI, but also from STAR. Kristin Nastras had a nice presentation. And we also had 3 presentations, I have here the rest of the agenda, from postdocs telling us about the direct experience with Rivet, of course, with the focus on the AI. So after me, there will be Marco Giacalone, who had the presentation at the workshop. And essentially, we will also give this, again, you talk about this experience with the usage of Rivet. The main outcome of this workshop is that Rivet looks to be the starting point for future comparison of results from supported event generator experimental data. We are about to release a summary of the outcome of this meeting, which we will add to the Indico page. And also we have the plan to have a second meeting, again, hopefully in person as soon as it will be possible, as the condition will permit. I think that that's all I wanted to advertise. I really thank you very much for your attention and the organizer for giving me this space. Thank you.
Thank you, Giuseppe. That was very clear, very informative. Still, there could be questions. Does anybody want to clarify anything with Giuseppe? It seems not to be the case. Well, it was very clear. One thing that we will have to organize somehow is to bring the slides on the Indico page such that everybody can, for example, have a look at the links that you provided. This is not the case yet because I think only very few of us have an Indico account at ECT Star. So this we will organize, and then in the next days, the slide.
I can either upload myself or send to you the PDF.
Yeah, if you send your slides to me, I can upload them for you. That's fine. So all clear to everybody? I think this is really a great opportunity, and we as a community should really make use of that. So thank you, and we turn to Marco, right?
Yes, can you hear me?
Yes.
Hello, let me share the slides.
And you will tell us about Rivet.
Yes, I will talk about my experience with the framework. So, can I start?
Yes, please go ahead.
So, good afternoon, everyone. I'm Marco Giacalone from University and INFN Bologna. And in this presentation, given on behalf of the ALICE collaboration, I'm going to guide you through my adventure with the Rivet framework. Can you see the cursor as well? Okay. So I started working with the framework in June 2019, since I won a 6-month grant in that period. I had totally no previous knowledge of what Rivet was, since my master thesis was on a completely different subject. I had some basic knowledge of the Monte Carlo generators, and I was also good enough with the C++ at that time, though. In my mind, Rivet was indeed the mechanical fastener you can see here on the right in the slide. The tasks assigned for the grant were to learn the framework, create macros containing ALICE Evil Flavors analysis, upload them on the Rivet website, since none of them were present when I started, and compare the obtained results with different Monte Carlo generators and different tunes. As computing resources, I had only my laptop at first, and later an ALICE server at INFN Bologna, whose specifications are shown here in the slide. So let me just talk about the software itself. Rivet is an easy and powerful tool that lets users compare Monte Carlo data to experimental ones. This is really useful because it lets us validate Monte Carlo generators, for example. In my opinion, the framework is also a great educational experience. As a matter of fact, as it was for me, in principle, you can produce a Rivet macro and compare Monte Carlo data in a really short time, learning a lot also about simulations and experimental results by reading lots of papers and understanding them deeply. The plot on the left is a typical result you can obtain with the software. In this case, it's a D+ cross-section from LHCb data. And on the bottom right of the slide, I'm showing the actual situation of the wanted analysis in the framework. As you can see for yourself, a lot of all the analyses are required and only few are already provided. Regarding the use you may do with Rivet, physicists may have different points of view. The experimentalists can say, for example, are the obtained data coherent with those obtained from simulations? While the theorists may say, can this new model I just developed better describe the experimental results? Well, then it seems they actually have a common aim, which is indeed comparing data, a thing that is done really well by Rivet. The only asked prerequisite for the software is to have Monte Carlo data in FMC format, which can be obtained with a lot of Monte Carlo generators already, like Sherpa, EPOS, Pythia, and Derwick, for example. Unfortunately, though, the system is not perfect. There are some issues. Firstly, installing the framework sometimes can be really painful. It took me some days in order to make it work on the server, since there was always a software prerequisite missing. The procedure, though, is much easier using Docker containers, even though this might be a little bit tricky using Windows subsystem Linux environments. Previously, also, the Rivet documentation, at least up to the version 2.7.2, was not very well updated. So indeed, I had to discover a lot of new features by chance through conference talks and looking also at the Rivet code itself. Regarding this point, though, things have changed a lot after the release of Rivet 3, and also thanks to much more interest by the community, which led to more workshops and more tutorials on how to use the framework itself. And then lastly, some useful application like Agile and Sacrifice for PTA 6 and 8. Those are interfaces to use those Monte Carlo generators. Have no documentation at all and are quite old. For instance, in order to make Sacrifice produce pilot collisions, I had to manually tweak the software because the Sacrifice wasn't able to do that. On this issue, actually, I've got a good example to show you on the next slide. So let's suppose we want to install the Agile software in order to run PTA 6 on our computers. So we just go to the Rivet web page, click on Agile, and then we have something like this. So let's suppose that we are not able to install the Agile software properly. So we want to click on the documentation. So we do that, and this was what I got when I actually tried to install Agile for the first time. So let's try to open a ticket then. We click on the ticket part here, and this is what we got. So in the end, I actually surrendered and I was not able to install Agile properly on my computer. But Rivet developers, after speaking, with Rivet developers in one of the last CERN Rivet workshop that Giuseppe was mentioning, it was made clear actually that Rivet is updated pretty often, and older Monte Carlo generators and their interfaces might have some compatibility issues with the newer version of the framework. For example, the support for Agile has ended in 2015, and Sacrifice support will end shortly. This is a double-edged sword because from one side, it's great that the framework introduces a lot of new stuff and fixes constantly some issues. But from the other side, this might actually cause some issues in revetizing properly older analysis, which require older generator setup. Moreover, actually, the Agile web page was updated a few days ago, and neither the documentation link nor the ticket requests are available anymore on the website. What you saw was actually screenshotted like 3 weeks ago. So you won't be able to replicate these wonderful errors I got. So let's now talk about the results I obtained. I worked mostly on PP collisions, and when I revetized my first heavy ion analysis in PLED, I found some difficulties at first due to the advanced Rivet function I had to use, and also to obtain Monte Carlo files from Sacrifice, which didn't support heavy ion simulations. To this, we should add also that Angantyr for PTA8 is quite an old model, and that working on heavy ion collisions on a laptop is extremely time consuming. Moving on to the analysis though, 3 revetizations were performed during my grant on 3 different papers. Those references can be found in the slide I'm going to show. So 2 were about D mesons production in PP collisions at 70V, and there are these 2 analyses here. And the last one was related to the lambda Siberian in PP at 70V and in PLED at 5TB. They are sorted in this slide from the easiest to the most difficult. The first one was basically just an example to understand better how the framework basis worked. For the second one, I had to use FIFOs in order to obtain data, and I had to merge them using the newly introduced Rivet merge function at that time. While in the last analysis, I had to use an advanced Rivet process, the reentrant finalize, which was introduced with Rivet 3. And I used that function in order to compute some of the plots required for the analysis, like the lambda CRP-LED. I did this analysis before the valuable paper confronting experimental data with heavy ion models, which is linked in the slide, was released. So it was even more difficult at that time. I'll show now some examples of what I obtained. For the D meson second analysis, I used 2 Monte Carlo generators, PTA8 and RVIC7, and 3 of the plots are shown here on the slide. 10 million events were generated and analyzed in order to have enough statistics. And in this case, I had to merge multiple jobs without manipulating data, which was difficult at first, but kind of easy when I found how the merge function worked inside the Rivet. As you can see, the obtained plots are looking nice. And in particular, here I'm showing the production cross-section of the D0, of the D sub S, and the ratio of the D sub S over D0. For the lambda C analysis instead, things were more difficult, as I told. I used again PTI8 and Derwig 7, but this time I also used the enhanced color recognition tunes by Christiansen and Scans in order to check whether or not there was an increased production of chart variants. And as you can see in the plots here, the tunes used, are indeed closer to experimental results. 1 million events were analyzed, but the problem with this analysis was that other than merging multiple jobs of the same kind, I had to merge also different simulation conditions. So PP at 7 TV, PP at 5 TV, and the PLED at 5 TV in order to obtain the final results, like the RPLED you can see on the plot here on the right. This was indeed difficult since we had to use the reentrant finalize to compute the plots, and I had totally no clue how to do that since the documentation on that particular function was totally absent at that time. In the end, I was able to get in touch with the Rivet group, which explained clearly how to solve my issue after some time. Moving to the conclusion, I can say that Rivet is a very incredibly powerful and educational instrument, given the opportunity to get closer to various experimental analysis, Alice in my case. Apart from the installation, I would say that it's actually easy and fast to learn, and the results obtained with it are clear and standardized. But unfortunately, there are some drawbacks. Most of the comments I'll make until the end of the presentation are based on 2019 outdated perceptions. So the situation may have changed for people who approach Rivet for the first time now. From my experience, the validating process seems to be very long. As a matter of fact, the results I obtained were uploaded after around 4 months on the Rivet repository. Speaking with the Rivet developers at the last CERN workshop with Rivet, they actually told that Rivet developers upload all the analysis once every 3 months, apparently, since 2 years. So then for a common user which was not working for a big experiment, so a big experiment that might have, for example, a big Rivet group inside, it might be actually difficult to understand from the Rivet website who to contact for clarification and issues fixing. So for this, it might be useful, for example, in the future, a public communication channel for this purpose, like a Discord server, for example. And then I think that more efforts should be put on helping new developers, like online support with assigned framework experts, and also more documentation on the linked application like Agile and Sacrifice, even though they are quite old now. So thank you for your attention and enjoy your Rivet journey.
Thank you, Marco. That was actually quite interesting, I must say. I had a similar experience.
Oh, perfect.
So, does anybody have a question or comment for Marco? Please raise your hand or just open your microphone and speak up. Pietro, please go ahead.
Yes, thanks, Ralph. It's more a comment and a question for the audience than a question for Marco. First, I would like to comment that there is something that Marco said in the presentation about the potential that Rivet has, I would say, in terms of being pedagogical. And this is something that we shouldn't underestimate, because the experience for Marco, maybe Marco wouldn't agree, but I think it was very positive in the sense that he was just graduated with a master thesis on a very experimental work on an electronic card that we developed. So he was in the condition to be a student which didn't have a connection with the analysis of the detector and the possibility of playing with Rivet, but before studying the papers that he had the task to rivetize was really powerful in terms of a pedagogical exercise. And if we could have a Rivet working for this level of student, I mean, being graduated or just graduated, for our AV ion business, this I think would be really powerful to make much closer the phenomenologist and the theoretical community with the experimentalist working on data. And here I come to the question that as Marco said, of course, there is a lot of things to be done in terms of better documentation and better support if you want to go through this exercise. But still, I have a more fundamental question. Maybe Giuseppe has ideas about that. That when we go to simulation for AV ions, many of the models, at least in my understanding, don't have the possibility by construction to produce FMC data and FMC results. And if we wanted to connect this, we should have some perhaps we should work on some interface that is able, starting from a generator, to then have the transport, but then being back to EPMC data format. And this is where, at least at the time, as Marco said, we were unclear because we agonized a little bit with PTI8 and Agantir. But probably this is the area where I hope with this workshop and the project that Giuseppe introduced, we can do a big step forward. That's all. I hope. I suspect my comment was quite unclear, but that's it.
Yeah, thank you. I think it was clear. So. It is a great tool. I fully agree. For a beginner, it is a bit of a bumpy road, and that has to be addressed. Giuseppe wants to answer.
Yes, very short. Yes, indeed, Pietro, this was one of the things which were discussed. I think Elena herself, which is present today, was raising this point. This is something which have to be pushed to be investigated a bit. This is still a standard for the other community, not for us. Looks to be a format not really ideal for data sites. Another aspect, also in that workshop, Christina Masters, she illustrated us, she has a project with students with this pedagogical aspects, which maybe are less relevant in this moment, but they are very important. I agree with you, Pietro. Again, I will put on the Indico the link. This is already my slide. You can have a look at the presentations if you have done.
Okay. Good. Let me quickly check whether there are any further hands. Giuseppe, we just had. I don't see anybody else. No, there's nobody. So thank you, Marco and Giuseppe. And we can turn to the discussion of the homework results. That is in the hands of Qin Dong. Qin, can you share the slides, please?
Yes, of course. Yeah.
And then I would just hand over to you.
I hope this is visible to everyone.
Yeah, now I see your PowerPoint window, and now it's full screen and it works perfectly. Great. Thank you.
Okay. Yeah.
Please go ahead.
Sure. So yeah, I will. Yeah, the purpose of this is try to get this probably flash to everybody. But I think other organizers, Ralph, Paul, Xinyan, feel free to jump in and correct or adding any further comments. So I think these were the set of homework assignment before the meeting. We sent out actually the first version was January last year, like a month before the original planned workshop. After that, actually, we got most of the inputs before the February last year already, and but then it got kind of paused. And recently, about 2 weeks ago, we sent in the request to everyone just check the updates. And after that, we received some further inputs and also updates. So we'll probably quickly flash to you the comparisons and outcome of this all this works. But I think to my feeling, the purpose of this try to gather this together to probably stimulate the discussions in the following days, because I guess every plot that when we talk about differences, that's going to be a long discussion, and which will be the focus in the next 3 or 4 days. Maybe let me just go through the questions quickly, and then we can flash through the comparisons. And for all the groups, if you spot anything wrong or I made a mistake here, please feel free to jump in. Or if you have anything to add, also feel free to comment. In my view, also this is should be a also involving probably comparison plots. So I think through the whole week, we can still try to update them if we have received further input. So the list of questions are characterized in basically this pre-meeting question in 3 categories. First one is about the heavy quark transport and comparing the coefficients. We have 1A is the spatial diffusion coefficient, which is one of the probably highlight also here, and compare that as function of the temperature dependence. And for both charm and bottom, we have pretty much all of them from all groups on the charm. For bottom, we only have a few. And then we have the B and C is basically the momentum dependence of the friction coefficient and also the diffusion coefficient. And we asked actually for a detailed comparison on both the temperature and also momentum dependence in this kind of a MASH table. And in following comparisons, we only show a few kind of cut view at the fixed temperature positions and check the momentum dependence. So the second category is about the hadronization and the hadronic phase. And 2A and 2B is asking basically the IA or HAA and HV2, the ratio between the IA of the heavy quark over the heavy flavor hadron. Sorry, the other way, heavy flavor hadron over the heavy quark. And same thing for 2B is for the V2. And the 2C is the ratio for the say d meson spectra at the final freeze-out phase over those at the hadronic phase. So this is to check also the hadronic scattering impact. So we this is all test at the 30 to 50% 5 TeV lag collisions. And so third category is the transport simulation with a fixed imposed coefficient. Here, this mostly is on 3A. Actually, we only have one on 3B, which also here we mentioned it's optional, but probably the focus on 3A. What is asking is about trying to renormalize the diffusion coefficient, the spatial diffusion coefficient to 4, and for long-range approach, and then compute the IA and V2 of the charm quarks. And so I'll flash all these results first and quickly. I hope you can see the slide advance. Sorry. This is the first question, Q question one about the estimate on the charm diffusion coefficient, and we have this from all linear groups here, and also the latest calculations, which also plotted the data points here. And this is for charm, and next slide for bottom, we only have a few here, and so do we have? I cannot see it. Ralph, please just stop me if you see anything. Anybody?
Seen?
Yeah.
Yeah, this is Paul speaking here. Well, in fact, in our case, and I guess it is basically the same in most groups, and we have not plotted something specific for B. Simply, basically, you get kind of very similar results. Okay? So,
yeah, sure. I think the focus, I also agree, probably we get the charm first, right? To go. Yeah. Okay.
But to answer your question, there is no hand up.
Okay. Okay. I guess we'll come to this discussion probably tomorrow for check all the comparisons for models. And then the question 1B is the normalized charm friction coefficient, the A parameter normalized by the momentum equal to 0. And so we have most of the models. There's a few, I'm missing a few of them. Some of them provide the whole tables, but I haven't got a chance to plot in this way. This is a normalized case. And this is plotted at the temperature 160 MeV. And the next one is 200 MeV and 300 MeV and 400 MeV. You can see, yeah, the movements. And actually, just for convenience, I think if we want to, this is kind of my probably personal choice of the temperature regions. We can choose probably whatever point we want. We ask for this from temperature 160 MeV to 600 MeV, and the momentum up to 40 GeV. So that's quite a wide kinematic range. This is normalized for bottom. Similarly, I think we can probably just flash them quickly, and yeah, so all the question 1B is for the friction coefficient normalized at momentum 0, and the 1C is really the comparing without this normalization, so the absolute comparisons. And for the charm and at the 160 MeV, 300 MeV, yeah, here I only pick up 2 because I guess yeah, I didn't have most of them, didn't have all of them from all groups. But if you have readouts, also feel free to share with us and we can add them in. And this is the bottom. Yeah, this bottom is very limited. The 1C also asks for the momentum diffusion coefficients, the B parameter. What plot here is only the in the transverse plane, and for the charm at 160 MeV and also 300 MeV. And we do have also bottom from only PHSD. I think we're missing probably a few. There are a few groups that is. I heard also like LBT Sunshine is updating the results, and we'll try to put them in when we have them available. Okay. Any questions or comments?
I would have a question.
Yep.
I noticed. Can you go back to the 160 for the charm A of P, the ratio actually, the normalized A of P? So yeah, so here I see that PHSD has an interesting feature that you know, up to there's a maximum of 2 GeV now, and this plot that seems a rather small feature, but it really encompasses a significant low PT range. And I was wondering if Elena could give us maybe some insight of where this enhancement at low PT, the momentum dependence, could come from. It may not be trivial, so, but just trying to understand it. Elena.
I'm actually here, but how to say, I think maybe Taiso, who did this calculation, has a better idea to comment on that. Because right now, I think I see this comparison for the first time. So before you send it, let me think, where could it come from? Maybe also the fact, I think that what we used for these calculations, we use not full spectral function, but maybe Taiso used kind of Breit-Wigner reduction. So he neglected in the, let's say, P dependence in the bulk particles. But that might be Taiso can comment better. Sorry. I really have to think and to discuss with Taiso what he actually did.
Okay. Yeah, I suspect I mean, what else can it be in a way than in a way the momentum dependence of the matrix element, right? Because
yes,
you know, this is the convolution of the thermal distributions with the matrix element. So it would point some non-trivial structure in the momentum dependence of the matrix element. I would suspect, but I don't know.
Yeah, but Ralph, you are absolutely right. But that's what additionally to that, you fold it with the spectral function of the medium, right? And that's what we figure out. If you come to low PT, that we know from other experience, it might change slightly behavior. And since you plot a ratio here, maybe somehow it's, let's say, artifact of this ratio. But okay, we definitely have to think with Taiso for the origin of this maximum. You're right.
Because this could be rather relevant in the low PT regime, right? That we discussed also this morning.
Okay, and since I'm talking, might be some question to him. If you come to some further presentation, would it be possible to change Catania color from yellow to some other colors? Because on this screen, it's very hard to see yellow color.
Okay.
Thank you.
Yeah.
Maybe I have a question. Xin, I forgot the when we did this, you know, homework assignment together. What is the scenario of, I mean, for example, when you calculate the coefficients, the parameter in it was adjusted to fit the brick problem, or whether it is just to fit dynamic fit to data, the data, final data separation factor.
I think mine, Ralph can correct me. My understanding in this calculator, we didn't fix anything, right? Did we? I just
we asked for the best current estimate in comparison to data, and
so again, you know, this looks like we are moving one step back, because we you know, in this report we finally published, at least within the heavy flavor jet working group, we find out that there's a lot of uncertainty coming from whether you have inelastic scattering or elastic scattering, and also different bulk evolution, and we're trying to isolate and then just look at purely within the brick problem. If you fix, for example, the separation factor in a brick problem, and then what you are looking at is purely due to the dynamic modeling of heavy flap transport. But now this come back again, this, you know, difference can include everything and essentially in the model.
Just wonder what is the definition? What is the definition of best estimate? That's
The best, I think the best is that in this case they use the model. Each model have different harmonization, have different initial condition, have a different bulk evolution, like hydro, for example, and then they try to fit the final data, and then this is the final transport coefficient they get.
So this is a feed to all the available data. Okay.
Yeah, that's what I understand. What Xin said, right?
Yeah, that's right. Yeah, we ask for the current best estimate and for each model.
Yeah, I think the effort, like within the heavy flavor jet working group, was trying to sort of isolate uncertainty, in these different models, where how much uncertainty is coming from the bulk evolution, how much is from hadronization, and how much is from the actually dynamic one.
Yeah, Xinya, I think generally I agree with the principle, but I think this is a kind of pre-workshop, pre-meeting homework to connect all this.
Yeah, I know, I understand.
I believe tomorrow and the following few days we do have we're trying to basically group all these different say components and then compare them individually. I think the big problems is indeed.
So this come back. So I think I want to bring out. I think we can openly discuss right now, right? There is no prefixed topic right now, right?
We are not quite sure with the figures, but okay.
So this come back to the question that I raised during the Minhurst's talk, and there he look at the hydro spectrum at right after the the freeze-out temperature, for example, and then for different the models, the bulk models, and then they vary. If I look at most of the group, they're already vary by factor of 2. But if you include in the one, I think that from PEDSP result, that's more than factor of 3 or 4, something like that. And then, so I ask whether those models are adjusted to fit the bulk spectrum, for example, the pion, kaon, proton, PD spectrum, and the V2, V3, for example. And that I don't know whether that has been addressed. Maybe we should find some time to discuss that, so that at least we can narrow down the uncertainty due to the bulk, which is not related to heavy flavor transport.
There is a raised hand from Elena.
Okay, I just wanted, maybe we discuss it later, but I just wanted to say that in our case particular, you see, I think it's more related how you treat a medium, because PhD result is very close to result of Catania, as it's a features how you treat your also medium. It's a quasi-particle response. And in this case, it's react differently like PQCD medium, which is depicted in the other models. And related particular to PhD in comparison to experimental data, of course, it's microscopic transport approach compared to all observables. And we are doing really, I think, rather good with the medium to be compared, to be applied for charm sector. But we can discuss it later, just short comment to your question.
Oh, yeah, but I think we're trying to isolate which uncertainty coming from the bulk, independent of the heavy flavor probe or not. And so in this case, I think by looking at the comparison of the bulk of the model to the existing, bulk hadron spectrum, which has been very precise right now. I think the most precise data available for bulk spectrum V2 and V3, and even fluctuation of the Vn, for example?
Hinyan, I think it comes, let me repeat again, these differences, let's say, comes mainly from the properties of your medium. And that's, if you remember our study, our activity, and that's what Jörg Eichelin reported, actually, it's very well understandable. It's related also to the behavior of your interaction of charm quark with the medium, how your coupling constant looks like, I mean, thermal coupling constant versus the PQCD coupling constants, which depend only on momentum, not on temperature. And the differences are related to this part mainly.
So, Irena, I think maybe
dynamics is under control precisely by plenty of observables in heavy ion collisions. Okay?
I think I'm not quite sure what I made myself clear. I said I was referring to the one slide in Minher's talk. In his talk, he summarized a comparison of different bulk evolution models for the bulk hadron spectrum. That has nothing to do with heavy flavor. Yeah.
Yeah, maybe we should. I mean, actually, you know, the idea, frankly speaking, was quite deliberately that we don't discuss too much the bulk in this meeting, right? We have a discussion allocated on the last day, but really, I think what we are trying to focus on is the microscopic ingredients. I mean, one thing that one can take away at this point is that the momentum dependence, the transport coefficient, is rather strongly varying between the models. You know, that needs to be figured out independent of any bulk evolution, right? I mean, fit or not, it's not even so important. I mean, this is a principal question. What is the momentum dependence of the transport coefficient, and how can we constrain that, right? And in the same spirit, I think we also wanted to address the question of hadronization and the question of the hadronic phase in the plots that are still coming. And not you know, circle too much back to the bulk evolution, which we know is an issue, absolutely. I think, and maybe Steffen Bass actually sketched the way going forward, that we use one of those that maybe we can agree on, that a large group can really use one of those as a common baseline, and then we're done with that. You know, I think that was not so much the focus right now of the homework activities, really.
I think your proposal is I think I would agree with your proposal. Like maybe one should, you know, when we do this homework, maybe one should use a common hydro profile trying to fit data, because without doing that, I don't really know the difference, how much difference of this coming from because of the adjusting each model with different parameter and with different hydro, you know. I think that the point is to, when I look at this difference, we should address how much difference is really due to dynamics of heavy flavor transport, or how much is due to, for example, hadronization, how much is due to hydro.
Yeah, we know that the bulk evolution model is a large area of concern, and you know, that remains the same, I think, up to now, more or less. So what we're trying to focus here is try to focus on other components, such as things like the momentum dependence, which shouldn't be a fit parameter, right? There is some answer on what the momentum dependence is from QCD, and I think we should try to figure that out, right? Independent of whether.
Yes, I completely agree, but without knowing, the problem without knowing the uncertainty from other things, that we don't, you know, when we discuss this, we can only discuss about this difference maybe qualitatively, but when you want to do a quantitative comparison, and it's kind of difficult to do that without you know, isolating uncertainty from other aspect of heavy ion collision, which is not really related to heavy flavor transport.
No, I think we ought to be able to get as much as information as
I hope so. I hope so. I hope we can continue. Okay, this is.
Yeah.
I just want people keep this in mind when we discuss when we do have a quantitative comparison. We should keep this in mind.
Mm-hmm.
Right, but there should be other pieces of information than comparisons to data, right? And this is, I think, what we want to find out here. You know, if I look at the momentum dependence and see a factor of 5 or 6 difference, there got to be some guidance from QCD on what's the more realistic dependence, right? Other than trying to fit to data, right? And that, I think, is the idea here, that we try to find information other than fits to experimental data that help us constrain the ingredients in the models, such as the microscopic calculations of the transport coefficient, the way we do hadronization, or the way we do diffusion in the hadronic phase, right? I would like to actually prefer to get away a little bit from the constraints from experimental data, but look for other constraints that we have from the underlying theory, right?
If I remember correctly, Xinyan, the purpose of doing this task number 1 and task number 2 was a bit to offer kind of the mirror comparison to what we did in this heavy quark working group, where I decided to put this tune 2 by gathering all models at p equal 15 GeV, okay? And here what we wanted to do was to say, okay, let us try to nail all the models around this 2PDS equal 4, roughly, and see what are the residuals difference between the models. This was somehow the initial goal of this homework proposal.
Mm. Anyway, I just want to remind us we have to keep that in mind. But come back to this problem. It looks like you know there's this coefficient can be divided into two groups. One is Catania and PHSD, and then the rest of this group. I think maybe Elenia is right, because the Titania group and the PHSD has some kind of similar like dynamics involving bulk evolution, right? They
Let me comment, Jan. I'm Vincenzo. Can you hear me?
Yes.
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 No, apart, I mean, when you show this in a normalized way, is somehow misleading in the sense that it seems very strange that you are able to reproduce more or less the same charm observables with such a different drag coefficient. However, if you go to the non-normalized one, maybe if you see that at the end, consider, for example, Tamu and Catania, and consider also that the kind of observables that we have looked at are things below 10 GeV. We have never used this above 10 GeV. So at the end, what happens is that on average, the value of the drag in the region where we look at RAA, in the region, let's say, where collisional dynamics should dominate, is not that different. This is one point. The other point is that the reason, so, I mean, if you plot this, of course, up to 40 GeV in a normalized way, then you have really that huge difference. But if you now look below 8-10 GeV, I mean, you can understand that, for example, things like Tamu and Catania that were very different in that plot here, at the end, you can understand why they can give a similar result on an observable, quite inclusive like RAA. On the other hand, the reason I think why we have a very slow PT dependence that just by hand, I don't know what is the right one, I would say cannot be realistic for sure up to 40 GeV, is because essentially it's a model in which you have very large thermal masses, and then you don't have explicitly a momentum dependence a Q square of the coupling. So essentially, you don't have this that at very large PT goes into the perturbative QCD result. So I think that is the. Now it seems that if you look at the RAA or V2 below 10 GeV in the region 3, 4, 2 GeV, then at the end you don't realize too much this directly if it is right or wrong. I would say that if you go up to 40 GeV, I don't think our approach is really reasonable. I would expect that the drug goes down because essentially in our model, how we build up our model, we fit the coupling to the thermodynamics of lattice QCD, but that is more in the region of the bulk of the charm, if you want, and light quarks, so it's around few GeV. I stop here. I don't know if it's clear, my comment.
Vincenzo, I think it is a great comment, but then don't you think one should restrain a little bit the range of PT where one provides prediction for the models?
Yes, but in fact, we maybe do the plot just because we are forced up to 7, 8 GeV, but we say that we don't even have also the radiative energy loss, but that is another point. Then I don't know exactly when it goes to PQ. I would say that 20, 30, 40 GeV, I would guess that is the right one. So, I mean, I think our approach is a reasonable approach below 8, 10 GeV. That is for sure. Then it's difficult to assess in the sense that we don't really have till now an observables that tell us no, that is a wrong P dependence. If I look at the V2 in the peak region at 2, 3 GeV, this I think is our status. And at the end, if we look at what Mine has shown, for example, Tamu and Catania are not so different from the point of view RAA. Of course, the details are different. Okay, that is.
Mm-hmm.
Yeah, maybe you should use go ahead to the section of the comparison.
Okay. Yeah. Okay. This is a set of comparisons for question 2A. The ratio of the hadron IA over the charm quark IA at the hadronization point, and so you can see the variation between different models, and do have nearly all of this collected here. And yes.
But then, this means that because we had already a quite similar plot in the EMI rapid reaction task force, but it seems that for a large PT, most of the models now they have something that is above unity, while it was clearly below unity. Or is there some subtleties that I'm missing here?
Any comments? Let's see. Some.
I mean, you had this plot in your presentation, right?
The IA of the.
Yes. In the high-level task force, we also made such a plot.
Mm-hmm.
What's your question, Paul?
No, the question is with respect to the plot. I remember from the EMI report, at large PT, most of the curves went up because we at large PT were typically in the same group of other models. We haven't changed anything to a hadronization model since then. And what I see is now all the curves went up, and this is everything. Okay, we will discuss this on Wednesday.
Yeah, this is also different when I remember from Minher's talk. There, can somebody can you bring up the same slides from Minher's talk so that we can check that this is the same?
Yeah, you have to share. I don't have your slides here.
Okay.
Yeah, let me stop.
Yeah, I have it in front of me. I could share. I mean, you want to do it or should I?
I have this one.
Okay, good.
Yeah, this is that's I think Paul said it true, because most of this curve is below 1. Maybe, yeah, at high PT.
So what is the deep reason behind this?
So now we go back to Xin's slides. Can we?
Maybe you have to unshare. I cannot share at this moment. So, thank you.
Yeah, this is definitely something different, right? This is all above 1. While in Minher's slides, most of them are below 1.
Is it the centrality that makes a difference? Because it's a 30-50.
Could this be some kind of factor?
No, the centrality does make it.
Is the centrality different? This is a
collision energy is also different, right? So
yeah. No.
Okay.
They are differently defined.
Yeah, but
that shouldn't
this HAA, it's defined as it's the you can say this is
yeah.
This is the ratio.
Upper differential.
The ratio. This
of
is the ratio of the ratio.
Yeah, ratio.
Ratio of the ratio.
Okay.
Yes.
And then you Minher's is just a ratio of the spectrum alone, right?
Exactly.
Oh, okay. Okay.
Okay. Any further comments or questions? I think we'll probably go into details on Wednesday on this topic.
Sorry, I'm Plumari. So just a comment about the Catania relation, the yellow curve. So essentially, this calculation was done with including the lambda C production, and you can see that this ratio is approximately up to 1 for transverse momentum greater than 5 GeV, something like that. But if we, for example, don't take into account for the lambda C production, this ratio becomes more or less with a peak at about 3 GeV, more or less, with a peak of 1.5. So essentially, just a comment. So the fact is that this ratio is smaller, maybe can be also due to the hadronization, essentially. If one assume also the lambda C production, if one include also lambda C production.
Yes, I agree with you. I think it just means, just implies a substantial part of charm goes to lambda C in your hadronization treatment.
Yes.
Yes, and that is part of the hadron, right? That we get the hadron into different states, right? And lambda C is of course a key ingredient, and it should be there. So I think your curve is fine if it's good if it includes the lambda C.
Sorry?
I think it's a good thing that you include the lambda C.
Yes, no, but the comment was essentially that if we include the lambda C, we get a reduction of this ratio. If we include lambda C, we get that this ratio is approximately 1.5 at 3 GeV, more or less. So similar to more or less TAMU and Duke.
No. The lambda C is also in our calculation. So.
Yes, we also have.
But in TAMU, lambda C is also included, right?
Yeah, we have that.
Okay.
We have that full chemistry.
Yeah, next slide show the comparison of lambda C. You see that this is the.
Okay. I have a question.
comment on it.
Yeah.
Well, go ahead. Maybe I just very brief comment. I think for lambda C, things are a little bit complicated because it involves some kind of like transport of net baryon into the central rapidity. So maybe one should also look at the anti-baryon, for example, like proton, anti-proton, some other, because that's sort of more relevant to the pair production from the vacuum or fermentation, but rather not closely related to the baryon transport to the central region.
No, but at LHC, we have a completely symmetric situation, right? So there's no issue here.
To be symmetric.
Yeah. Sure. If the baryon anti-baryon is more or less symmetric, then that's a different story. Yes.
Yeah.
So what is the difference between TAMU1 and TAMU2 here, if I may ask? I should know.
Ming, you want to comment? Yeah.
Just uncertainty. We can say a significant uncertainty from the treatment of branch ratio. So if we excited the charm barons when they decay into the ground state lambda C.
Okay, thanks. So that's the error band we usually show.
Right.
Yeah.
Okay.
So this is dramatic difference. I mean, how far up does the LBT go?
You mean the momentum, PT?
No, the peak. I mean.
The peak. Yeah, I cut it off because I got it from Shanshan this morning. I was very rushed. I didn't make modifications, but I think Shanshan will probably send out an update later on in the weekend. It's yeah.
Right.
Okay. So this is on the V2 part. Also, this is double ratio, the ratio of the V2 of quark heavy hadron V2 over the quark V2. I think it's a little bit noisy because I guess many models have there are lots of fluctuations. You can see the regals. I don't. Yeah. But okay. And lambda C only have a couple of them here, and interesting. The LBT is also just a newly added. I think we probably will continue this discussion through the week.
No, but what you immediately see in this ratio is how going from a meson to a baryon, you get a significant increase in that ratio, right? Because the lambda carries two particles from the bulk here, right? Sure. And that really makes the ratio significantly enhanced, basically, right? Over whether you pick up one or whether you pick up two. So here for the lambda C, it's around 4.5, 5, and on the previous one for the D, was
2.5.
Our calculation like 2.5. But the other calculations didn't really pick up that much.
Okay. Any further comments? So, okay. Let's move on. The question 2C is about the hadronic effect. I only have two of them here, and it's seem to be rather relatively small, but I think we can discuss details.
Yeah. So here I have a question to Elena. She mentioned earlier that the effect is relatively large in PHSD, while I mean. So it's not small, but it's mostly at high PT. Or what is your take on this when you look at this, Elena? She's still around? Yeah.
Yeah, she is.
On our calculation, basically,
may I answer?
Yes,
if
please.
I remember correctly, hadron effect is strong at Rig energy, and at HC energy, I think the relatively the hadron scattering doesn't have a strong effect compared to Rig energy.
Sorry, you mean at LHC?
Yeah, at LHC energy, hadron interaction has a less strong effect compared to Rig energy.
Okay.
That is what I remember.
Okay, thank you. Yeah, and it's clear. I mean, you get a little extra suppression at high PT, and then you do see the flow bump that the hadrons, also augment just a little bit. So the structure is straightforward. Yeah. Of course, there's some fluctuations, but that's fine. Okay.
Yep. Okay. So I guess I mislabeled this. Oh, this is V2. Yeah, ratio, not mislabeled. Sorry. Yeah, that's right. This is the ratio of the V2. Also, kind of.
Yeah, here's a big effect.
Yeah. Yeah. Okay. So the question 3A is calculating using renormalized spatial diffusion coefficient, and this is a connection of the calculations for I think probably linear groups here available here, and
sorry, may I ask to go back to the V2 just one more?
This one.
So yeah, so this is a rather big effect, right? 40% increase in the V2 from the hadronic phase. I mean that reiterates what Steffen Bass said, that the hadronic effects may not be all that small. At the end of the day. And it gets pushed out, of course, so that also makes sense. But yeah, there. Okay, thank you.
Okay, this is IA on the charm quark and V2 on the charm quark, and I think that's all we have collected. And yeah, some groups also send out probably not just one calculation, maybe two calculations with different choices. We can try and find a way how to display that, but currently I probably just picked one of them here, which I feel is probably more appropriate, but feel free to comment adding.
Yeah, this is quite interesting, actually.
Yeah.
So, if you do the constant ds and then work with your momentum dependence, it means that you, relative to what we usually have, you're emphasizing more the earlier phases relative to the later phases, right? Because usually the ds decreases with temperature.
Yeah.
So in the PHSD, it seems you get a lot of juice from earlier phases, and in other calculations, you're actually getting less juice. For example, LBT or also TAMU, they don't they have less than what they would usually get. PHSD seems to be, and also NONCH seems to be getting quite a bit from earlier phases here.
I think the large electric flow is caused by momentum dependence. In this scale, we scaled only the ds at zero momentum. I mean, ds is calculated at zero momentum, but the momentum dependence of drag coefficient is important because most charm has large, not small momentum. So actually, it's not, in my opinion, it's not an ideal comparison because momentum dependence is neglected in this case.
But Ralph, I agree with your point, but then I guess what we should do is also to plot what we get for the usual embedding in the hydro, and then we can see the relative influence.
Yeah, sure. That was the idea, right? That you vary the temperature dependence of ds and then see what the relative effects are. So yeah, one could do that plot, absolutely. Compare, compare more directly, maybe with a couple of more plots, one by one, what the change in the temperature dependence here does. That was exactly the point, absolutely. But let me ask Tezu again. So you renormalize the S, but you keep the momentum dependence of your original model or not?
Yeah, I kept the original momentum dependence. I just multiply by a constant factor such that ds is
that's exactly what the idea was. Yeah, and this may actually indeed reiterate that the fact of the momentum dependence that I pointed out earlier at low PT, right? Because in this 2, 3, 4 GV momentum region, your momentum dependence has this this increase, right? And maybe that's what correlates with what we're seeing here.
Yeah, I'm not so sure, but I guess that strange behavior near zero momentum is caused by a spectral function, because in principle, our calculation is should be similar to Catania group, because we use massive quarks and gluons, but the only difference is spectral function. We have a spectral distribution, but Catania is constant. I mean, doesn't have a spectral distribution, and I guess that difference is caused by that difference. Yeah, I should check, but that is my guess.
Okay, let me say what I meant. I wasn't referring to where it came from. I was referring to if you have it in there, you get this. So in this, so the question then is, in this calculation, do you have that feature in there or not?
What feature?
The feature of the enhancement of A of P at low PT. Is it in this?
I think in principle, there is here. I mean, I just multiply by constant vector. So the shape.
Well, that's all I'm saying, right? That's all I'm saying. And let's not forget, the region where it was actually around. Go to the 160. Not the bottom, the charm. Yeah. So this was over a region from 0 to 4 GV. Okay, let's not forget that this is from 0 to 4 GV, where other models start dropping already, and yours is more or less about 1, right? And this is more or less what coincides with when we go back to that V2, where you see the peak there, right?
Yeah, this is 2 to 3 GV, 2 GV. Oh.
Yeah, peak is it. So that is that region there. That peak more or less coincides with the peak in momentum dependence. I don't know, So maybe that's that reiterates the fact, of course, that the momentum dependence, especially at low PT, it's very important if you want to make a statement about the zero momentum limit, right?
Ralph, do you know the momentum changes continuously during time evolution? So actually, that around 4 GV is originated from 8 GV or more higher momentum. So it's not simple matter. I mean.
No, I'm not sure I agree with you. I mean, I'm not sure I agree with you, because the local PT, if anything, is smaller, right? I don't think.
But many large. I mean, the charm quark with the large momentum becomes soaked by interactions. So there are two contributions.
No, sorry. You can never get a significant yield from a high PT charm quark down at low PT. The exponential spectra fall dramatically. You will never feed in significant yield from an 8 GV charm quark into a 3 GV spectrum.
I didn't thoroughly investigate it, but in principle, there should be two different contributions. I mean, both contributions, not only from low momentum region, but also high momentum region can contribute to that area, around 4 GV, I think.
Yeah, the contribution from high momentum is very limited because of the steeply falling spectrum.
Maybe, but in principle, it's possible, and I don't know how much it would be.
Okay, Taifu, let me suggest you just remove that peak in the A of P in the transport coefficient around like a 3 GV or 4 GV, make it like a smooth drop, and then do the simulation again and see if this enhancement of in V2 as around the 3 GV disappears or not.
I can test, but it takes time. Yeah.
Okay.
When I comment on that, I think it's really impossible because transport coefficients, which Taiso has calculated, they are computed based on elementary scattering cross sections, and it's not transport coefficients and not input in our model. We are not doing hydro calculations. We are doing microscopic transport. Input is the differential cross sections in this case. And I also agree with Taiso. I don't think that this bump, which is in PT and then decrease, is related to the bump which we see in the transport coefficient at temperature close to hadronization point, because this bump appears at temperature close to hadronization point, and I also more related to the behavior of our spectral function, in particular, rapid increase of coupling constant closer to TC. So, and here I think what we probe, it's already high energy PT physics, and also this decrease, I also relate such fast, it's just statistical issue, because here we have a huge statistical fluctuation, and what is presented here, it's not in the real calculations like that, it's a huge statistical fluctuation, and here we show some averaging things with a very large bin, otherwise it's very time costly calculations. For us at 5 TV, it's incredible computational times involved in these calculations.